Hello there. Today we are looking at problem 39. Combination sum. Given an array of distinct integer candidates and a target integer target, return a list of all unique combinations of candidates where the chosen numbers sum to target. You may return the combinations in any order. The same number may be chosen from candidates an unlimited number of times. Two combinations are unique if the frequency of at least one of the chosen numbers is different. The test cases are generated such that the number of unique combinations that sum up to target is less than 150 combinations for the given input. Example 1. Candidates 2, 3, 6, 7. Target 7. Output 2. Okay, let's stop there. So let me read the question to make sure I understand the problem. So we are given an array of distinct int. So let's just call it candidate. Candidates is a integer array, and this is unique, meaning that all the elements appear just once. And target integer. Return a list of all unique combinations. We may return in any order. The same number may be chosen from candidate an unlimited number of times. So we need to return list of combination sum and allow repetition. So we are allowed to take a number repeatedly from the integer array. Now here, what else do we need to know? I'm thinking about what else could be relevant to know here. Alright, I think that's all. So now let's look at some example. Example 1, candidates is we just call it with C equals 2, 3, 6, 7. Okay, 7, and then target is 7. Output, now this would be, say if we take 2, so we could take 2, 2, 3, or it could be just 7. Alright, now example 2, candidate is 2, 3, 5. Target is 8. Now the output, this could be 2, 2, 2, 2. It could also be 2, 3, 3. Or 3 and 5. Example 3, candidate is 2. Target is 1. So output is just empty list. because there is no solution there. Alright, so I'd like to clarify a few things. Clarify. One, length of C. So what are the number of elements inside C? We know that. So the given that candidate's length is 30 at most, and there is at least one. Okay, so candidate is valid. And all elements are distinct. Okay, that is given. Target is 40. Correct. So I think I understand the problem now. Let me think about possible approaches. Okay. So I can think of a few possible ways. So one of them that I think is pretty good. One of the solutions that I can think on top of my head is to use we could use a list. So given that the target is limited, so here we know that target is okay. I think it's a good thing to clarify as well the range of target. So how large can target be? So it says that it is between 1 to 40. So target is quite small. So what we can do is we use an integer array. But you need to find out all the solutions here. So I was thinking that we could compute all the possibilities to get, say, to get 0, and then we add up all the values in candidates. So we then find out what are the ways to get the value 1, what are the solution to get value 3, so on and so on. But I'm thinking that it could grow very large. So I think that is not a good way to do. And in here we are given that, okay, but 1 second. Okay, so we know that we are given that the number of combinations is less than 50, 150. Okay, hold on, do I need to know that? Length of C is 30. So I'm trying to estimate like how complex this problem would be, because C is quite small, it's just 30, and then T is quite small as well, it is 40. So if it is 30, and then we grow it every time, I think it could be quite large. Then we move on. 16, 30 times 40 could be 1000. So 30 times 40 is 1,200. So 1,200 solution is quite large, but if we times it. Okay, so I think one way that I think the solution that I described earlier could potentially be memory efficient because the length of C is quite small and the range of T is also quite small. So if we think about it, the number of ways to get 40, it could be just at most 40 values. Say if we just take 1111 until we get 40, then okay, let's see. May I know? I think another thing that we could need to clarify is the value of C. Okay, or we could ask the range of Ci to see if there is any negative value because it could complicate things here. So we are given the candidates is between 2 to 40, so all of them are positive. So if we are given 30 candidates and we need to get 40, what are the number of ways if we could estimate them? I would say it is, let's see, is it quadratic? Okay, so I think it's factorial because if we try to iterate the candidates and then we grow it until 40, then I think there are, okay, so let's just assume that our solution will be sorted and it will be in a non-decreasing order. Okay, non-decreasing would be what we see in the example as well. So there are examples. So if we think about it, then the non-decreasing solution there could be like a 40 factorial. So 40 factorial is quite large, and in my solution that I proposed earlier, there are 40 values that I would like to iterate, and that would give us 40 factorial times, how many is that? 40 values. So yeah, still 40 factorial, but it's quite large. So I think I'm not gonna do that. Although it could be quite efficient in terms of that's our time. But let me think for a second there. I think a more efficient way, actually, if we need to find the solution there, then let's see. If we look at the examples, we have 2, 3, 6, 7, and we want to get 7. Then we could take 2, 2, then we could take 2 again, but then doesn't lead to anywhere. So we take a step back, we take 3, we got it. Then we check again. 227, 226, 227 doesn't work. Okay, so a few findings. If the solution doesn't work, if combination exceeds the target, then stop checking the next element. Okay? Because if we know that 226 won't work, then we don't need to check 227 anymore. Could just backtrace, backtrack to 23, for example. So 233 exit 7, so we just stop there, we backtrack. I think this could be a solution. Yeah, I think so, because we just need to recursively build up the solution. Alright then, I think this could work. And in terms of complexity, I think it could be quite small, because in here, you are given that there are 150 combinations. So and with this optimization, where the combination sum is larger than t, then we stop iterating, and then we just backtrack. So I think that could minimize the potential solutions to get the target. Okay. Alright, I think what we're gonna do is okay, I think we can do it recursively. So let's see. That is first we take an element, take ci. Actually, we take the target and then we decrease the target with ci, and then we could recurse for all I is larger or j larger than or equals to I. We try to recurse target. But first of all, we need to check if target is 0, then we record it. Otherwise, else, if target is less than 0, then let's see. Then we return directly. Stop. Otherwise, we move on to step 2, where we recurse the t. So if I try to work this out, work through these steps for the examples, what we are gonna have is that for the first example, I'm gonna have say 2. Okay, let me just write it this way. Curve and target. Curve is 0, target is 7. Then we basically move on to check 2, comma. Okay, let's do it this way. I'm gonna begin with empty. Then I will have 2, and then 5, and then I will also have okay, let me work on it one step at a time. So first of all, we get the empty, and then we need to check if we take 2, then target becomes 5. And then if we work on it again, this would gives us 2, 2, 3. Then from 2 to 3, we could build 2, 2, 2. And then this would be 1. Then this would give us, we need to check further, say 2, 2, 2, 2, 2, 2, 2, 2. It is -1, so we stop there, we backtrack. And then we would have like 3, 6, and 7, and then we backtrack too. So now there is no solution with 2, 2, 2. Then we move on with actually, how do I backtrack if I take the solution? So 2. Okay, so when I check 2, 2, 2, 2, I need to break. So break so that I don't check any further. And then I'm gonna backtrack. Now I'm checking 2, 2, 3. Let's give us 0. Now we add it into solution there. Solution. And then to, okay, when there is a solution, we could just break. So in here, we call break, because there is no point to check with larger values as we have found the solution. Now, the next step would be 2, 3. Then this will be 2. Target is now 2. Now we check 2, 3, 3. It gives us -1. So we break. After we break, we go back to 2, and let's say it's 6, is it? Now if we take 6, this would give us -1. Then we break here. After we break, we would have 2. Then we explore 3. If we take 3, then we need to find 4. When we try to find 4, we take 6. No, take 3 again. And actually at this point it is not -1, but it is less than the current value. Okay, so that is one more observation. So instead of t less than 0, t is less than ci, then we break. So after we break, now we explore with 6. 6 is 1. Now we break it here too. Okay. Actually in the future, here if we break it, then we miss the 7, which is another solution. So we cannot break too early then. Yeah. So we cannot break too early. 6, 1, break. 6 is wrong. What we need to do instead is explore further. So in the beginning, we have 3, 3, 1. The next one would be 3, 3, 3. And then -2. We break here. And then we need to explore 3, 6. This gives us -2. Then we break here. Okay. After we break at 3, 6, now we explore 6. 6 gives us 1. When we try to look for 1, we are gonna encounter 6 again. 6, 6. And this will be -5. Then we break here. Then there would be 7 at last. There is 0, solution, and break. Okay, I think that's about it. Now let's try with the second example. We have C at 2. So if we take 2, let me just simplify my writing. And 2, and D, 7. That's 8 there. Okay, 8. I think it's enough to go through one example because it takes some time. Sorry. Okay, and I think we just go through the example anyway. So let's see. I think a better way to represent this is we take 2, and then next step we take 2, 2, 2, and then 3, stop. So go back, take 3, and then we take 3 again. So we stop there. Say 2, 2, 5. Say, yeah, this is not just so we stop there. Now we take 3. And we take 3 again. This is a solution. So this should not be blocked. Yeah. So now 3, 3. Now we try with 5. Give us 7. So 5 again. This does not give a solution. And then try with 2, 3, 5. Okay. So everything that works with 2 in the beginning stop working. And now we check with 3. 3, 3. Stop there. Try with 5. This is a solution. And then see. So we stop there. We try with 5. 5. That's it. It's not solution. So we have 1, 2, 3. Yeah. Correct. Third example. We have 2. Then we stop there. So that's it. Does it sound reasonable to you? I am pretty good about this and I would like to start coding unless there is a further optimization that you would like me to explore. Alright, let's do this then. How are we gonna do this? So I'm thinking that we could do this iteratively better. Okay, there I got one idea. So what you're gonna do is you're gonna create an output list. It begins with empty, and then I'm gonna create a function that I call recursively. So define, what do I call it better? I think I just call it, let me see. Just call it F for simplicity. Yeah. So F, then we have candidates. We also have target, and then we need to store the curve. So now what we are gonna do is we look through the candidates or see in candidate if target let's just call it output here or let's say on the I'm trying to think of a better variable name. Candidates, target, and so chosen. Okay. For C in candidates, curve minus equals C. In curve is 0, output dot append the current solution chosen plus C. Okay, and if curve is larger than 0, if curve is larger than 0, then what we're gonna do is we need to recurse it. But first of all, we need to recurse at the candidates, but we don't want to recurse the candidates before C, so it has to be C or larger. So how are we gonna do that? I think we just use an enumerate here. So for I, C, enumerate, then I'm gonna call f of candidates of I. So from I onwards, and then curve, then this would be chosen the append or I think I need to make a copy here. So chosen plus C. Alright. So now else we break it. Then at the end we return f of candidate of target chosen is empty list. Alright, now let me quickly go through the code again to make sure I don't miss anything. I'm gonna do this recursively. First of all, I create the output list. Then in the recursive function, I will need the candidates, target, and what I have chosen to include in our current solution. So in here, I will enumerate the candidates, check the target. I'm assuming that I am taking the current candidates. So what are the next target that I need to fulfill that target? If the target is now becoming 0, then I have found my solution. So I open the chosen, what I chosen previously, and then I open C into it. Okay, something very important is that I forgot to break here. Yeah, because if I found the solution, then I don't need to explore the next candidate in the current with the current given list. Otherwise, if the current is still larger than 0, then I need to recurse it, try to find it. Hopefully in the next recursion I'm gonna find the solution. So that's what we did. We call the function, but don't forget that we don't want to check the previous candidate, the candidates that are smaller than the C here, because otherwise it would be a waste of our computation, because that has been explored previously. And don't forget we append the C into the chosen. Otherwise, if current becomes negative, then there is no need to further explore on this part. You just return it. Now, let me test the code here with our example to make sure it works as expected. First of all, we call the we call the candidates target and empty list. So right now, if we look at the example 2, I have 2, then curve would be say 6. So I recurse it 6, and then 4, 2, and then at the end, at one time, I'm gonna get curve 0. So now I append 2, 2, 2, 2 into my solution. And then the next time, I'm gonna try with 2, 2, 3. After that, it would be 2, 2, 3, 2, which does not give me the solution. So I will stop there, and then we try with 2, 2, 5. We don't get the solution either. We stop there. Then we try with 2, 3, 3 in the next loop. So if we try with 2, then 3 give us 5. So target becomes 3 now. So I'm gonna call candidates I from I to the end. Actually, I don't need to recreate the candidate string. I could just use an index. So I'll do that when I code the LeetCode. But let's move on with the example. So we have 2, 3, 3. We found the solution. We stop there, and then we try with 5 to find 5. Doesn't work. In the end, we have 2. After that, we will check 3, 3, 3. Doesn't work. 3, 5. It works. Stop there. 5, 5. Doesn't work. Alright, so I think that kind of makes sense. Now let me try to work on it in the LeetCode. So output start with empty list, then define f index target and chosen. one very small optimization is I can use a deck in the chosen. But then I do that later. So curve for let's say let's see candidates. Let's just start here. For I in range start comma length of candidates. Okay. So start is the start index from when we use the candidates. Curve minus equals candidate of I. If curve is 0, then output the append chosen. So I think what I could do is chosen. Let me try to check if I could create a list out of Python deque to list. Okay, so I just call a list on the deck. So chosen.append. So is it candidates I. Yep. And then append the list of chosen. After that, I'm gonna remove the element. So chosen dot pop, and then we click. Yep. If curve is larger than 0, then we need to explore further. F of I curve. Can chosen be put outside? Yeah, I think so. Chosen is the deck. Alright. So here I'm gonna comment local chosen and output. Curve else I'm gonna break it. Okay. Now here I'm gonna call the f start at 0, and then we want the target. Then we return the output. So let's try this. This is wrong. Curve is not associated with our value. Curve is not associated. Okay, curve here means that the target minus candidate. We got a wrong answer there. Okay, so before we break into, let's see, person.append candidates. How come we have 3 there? And how about we print the list of chosen for debugging? Taking so long. Oh, it's all empty. What happened here? Oh, okay. Okay, got it. So we forgot to append it. Chosen.append the current candidate. So we got 2, 2, 2, 3. Target is 7. We need to put the candidates as outsider, as a non-local. No. Okay, so let's try to print Johnson and target. 7, 5, 3, 1. How come when we take 2, 2, 2, and 3, the target becomes 2? 2, 2, 2. We should have break there. Okay, I think a better logic would be if we put the code here, then we take it in the end when we break. Before we break, we need to pop it up. Yep. Okay, I need to check one thing about Python. Does Python break 6 one loops? Does Python break circuit remaining on loops? Okay, so it terminates. You see, I think this should work here. How is it not pop out? Okay, they got it. So instead of putting it here, I just put it here. And then I will put it here. After I explore it, I need to pop it out. Okay, and here I'm going to pop it. And here I need to pop it out. So let's try that. Yes, this time we got it right. Let's remove the print, then submit it. We got the wrong answer here. Okay, the solution is not sorted, which I assume. So I made a mistake there. Sorry about that. Candidate equals sorted. Candidate string. Yeah. So let me put down the notes in my paper. So don't assume sorted is. Don't assume list is sorted. Okay. Yes, I think everything is looking pretty good. And we started to see what the solution looks like. Output system target. So I think everyone is doing pretty much the same. Alright then. There are some much more simpler solutions, but I think it's more or less doing the same thing, I think. So this one looks like the first, my first solution that I proposed. So it definitely works, but I'm not sure about the memory complexity there, because it could grow very large. So, alright then, I think I will stop here. Thank you everyone.